Hello everyone, welcome to my channel. Today we start another topic talking about special relativity. Episode 3 from Albert Einstein documents. Are you ready? Let's start together. This prompts Einstein to raise to the status of a postulate the principle of relativity, which holds that the laws of mechanics and electrodynamics are the same in all reference systems moving at constant velocity relative to one another. Einstein goes on to propound the other postulate upon which his theory was premised: the constancy of the speed of light, independent of the state of motion of the emitting body. Then, with the casual stroke of a pen, and the marvelously insouciant word, superfluous, the rebellious patent examiner dismissed 2 generations' worth of a crude scientific dogma. The introduction of a light ether will prove to be superfluous, inasmuch as the view to be developed here will not require a space at absolute rest. Using these 2 postulates, Einstein explained the great conceptual step he had taken during his talk with Besso. 2 events which, viewed from a system of coordinates, are simultaneous, can no longer be looked upon as simultaneous events when envisaged from a system which is in motion relative to that system. In other words, there is no such thing as absolute simultaneity. In phrases so simple as to be seductive, Einstein pointed out that time itself can be defined only by referring to simultaneous events, such as the small hand of a watch pointing to 7 as a train arrives. The obvious yet still astonishing conclusion: with no such thing as absolute simultaneity, there is no such thing as real or absolute time. As he later put it, there is no audible tick-tock everywhere in the world that can be considered as time. Moreover, this realization also meant overturning the other assumption that Newton made at the beginning of his Principia. Einstein showed that if time is relative, so too are space and distance. If the man in the carriage covers the distance in a unit of time measured from the train, then this distance as measured from the embankment is not necessarily also equal to w. Einstein explained this by asking us to picture a rod that has a certain length when it is measured while it is stationary relative to the observer. Now imagine that the rod is moving. How long is the rod? One way to determine this is by moving alongside the rod at the same speed and superimposing a measuring stick on it. But how long would the rod be if measured by someone not in motion with it? In that case, a way to measure the moving rod would be to determine, based on synchronized stationary clocks, the precise location of each end of the rod at a specific moment, and then use a stationary ruler to measure the distance between these 2 points. Einstein shows that these methods will produce different results. Why? Because the 2 stationary clocks have been synchronized by a stationary observer. But what happens if an observer who is moving as fast as the rod tries to synchronize those clocks? She would synchronize them differently because she would have a different perception of simultaneity. As Einstein put it, observers moving with a moving rod would thus find that the 2 clocks were not synchronous, while observers in the stationary system would declare the clocks to be synchronous. Another consequence of special relativity is that a person standing on the platform will observe that time goes more slowly on a train speeding past. Imagine that on the train there is a clock made up of a mirror on the floor and one on the ceiling and a beam of light that bounces up and down between them. From the perspective of a woman on the train, the light goes straight up and then straight down. But from the perspective of a man standing on the platform, it appears that the light is starting at the bottom but moving on a diagonal to get to the ceiling mirror, which has zipped ahead a tiny bit, then bouncing down on a diagonal back to the mirror on the floor, which has in turn zipped ahead a tiny bit. For both observers, the speed of the light is the same, that is Einstein's great given. The man on the track observes the distance the light has to travel as being longer than the woman on the train observes it to be. Thus, from the perspective of the man on the track, time is going by more slowly inside the speeding train. Another way to picture this is to use Galileo's ship. Imagine a light beam being shot down from the top of the mast to the deck. To an observer on the ship, the light beam will travel the exact length of the mast. To an observer on land, however, the light beam will travel a diagonal formed by the length of the mast plus the distance. It's a fast ship, that the ship has traveled forward during the time it took the light to get from the top to the bottom of the mast. To both observers, the speed of light is the same. To the observer on land, it traveled farther before it reached the deck. In other words, the exact same event, a light beam sent from the top of the mast hitting the deck, took longer when viewed by a person on land than by a person on the ship. This phenomenon, called time dilation, leads to what is known as the twin paradox. If a man stays on the platform while his twin sister takes off in a spaceship that travels long distances at nearly the speed of light, when she returns, she would be younger than he is. But because motion is relative, this seems to present a paradox. The sister on the spaceship might think it's her brother on Earth who is doing the fast traveling, and when they are rejoined, she would expect to observe that it was he who did not age much. Could they each come back younger than the other one? Of course not. The phenomenon does not work in both directions, because the spaceship does not travel at a constant velocity, but instead must turn around. It's the twin on the spaceship, not the one on Earth, who would age more slowly. The phenomenon of time dilation has been experimentally confirmed, even by using test clocks on commercial planes. But in our normal life, it has no real impact, because our motion relative to any other observer is never anything near the speed of light. In fact, if you spent almost your entire life on an airplane, you would have aged merely 0.00005 seconds or so less than your twin on Earth when you returned, an effect that would likely be counteracted by a lifetime spent eating airline food. Special relativity has many other curious manifestations. Think again about that light clock on the train. What happens as the train approaches the speed of light relative to an observer on the platform? It would take almost forever for a light beam in the train to bounce from the floor to the moving ceiling and back to the moving floor. Thus, time on the train would almost stand still from the perspective of an observer on the platform. As an object approaches the speed of light, its apparent mass also increases. Newton's law that force equals mass times acceleration still holds, but as the apparent mass increases, more and more force will produce less and less acceleration. There is no way to apply enough force to push even a pebble faster than the speed of light. That's the ultimate speed limit of the universe, and no particle or piece of information can go faster than that, according to Einstein's theory. With all this talk of distance and duration being relative depending on the observer's motion, some may be tempted to ask, so which observer is right? Whose watch shows the actual time elapsed? Which length of the rod is real? Whose notion of simultaneity is correct? According to the special theory of relativity, all inertial reference frames are equally valid. It is not a question of whether rods actually shrink or time really slows down. All we know is that observers in different states of motion will measure things differently. And now that we have dispensed with the ether as superfluous, there is no designated rest frame of reference that has preference over any other. One of Einstein's clearest explanations of what he had wrought was in a letter to his Olympia Academy colleague Solovine. The theory of relativity can be outlined in a few words. In contrast to the fact, known since ancient times, that movement is perceivable only as relative movement, physics was based on the notion of absolute movement. The study of light waves had assumed that one state of movement, that of the light-carrying ether, is distinct from all others. All movements of bodies were supposed to be relative to the light-carrying ether, which was the incarnation of absolute rest. But after efforts to discover the privileged state of movement of this hypothetical ether through experiments had failed, it seemed that the problem should be restated. That is what the theory of relativity did. It assumed that there are no privileged physical states of movement and asked what consequences could be drawn from this. Einstein's insight, as he explained it to Solovine, was that we must discard concepts that have no link with experience, such as absolute simultaneity and absolute speed. It is very important to note, however, that the theory of relativity does not mean that everything is relative. it does not mean that everything is subjective. Instead, it means that measurements of time, including duration and simultaneity, can be relative, depending on the motion of the observer. So can the measurements of space, such as distance and length. But there is a union of the two, which we call space-time, and that remains invariant in all inertial frames. Likewise, there are things such as the speed of light that remain invariant. In fact, Einstein briefly considered calling his creation invariance theory, but the name never took hold. Max Planck used the term relative theory in 1906, and by 1907 Einstein, in an exchange with his friend Paul Ehrenfest, was calling it relativitats theory. One way to understand that Einstein was talking about invariance, rather than declaring everything to be relative, is to think about how far a light beam would travel in a given period of time. That distance would be the speed of light multiplied by the amount of time it traveled. If we were on a platform observing this happening on a train speeding by, the elapsed time would appear shorter. Time seems to move more slowly on the moving train, and the distance would appear shorter. Rulers seem to be contracted on the moving train. But there is a relationship between the two quantities, a relationship between the measurements of space and of time that remains invariant, whatever your frame of reference. A more complex way to understand this is the method used by Hermann Minkowski, Einstein's former math teacher at the Zurich Polytechnic. Reflecting on Einstein's work, Minkowski uttered the expression of amazement that every beleaguered student wants to elicit someday from condescending professors. It came as a tremendous surprise, for in his student days Einstein had been a lazy dog, Minkowski told physicist Max Born. He never bothered about mathematics at all. Minkowski decided to give a formal mathematical structure to the theory. His approach was the same one suggested by the time traveler on the first page of H.G. Wells's great novel The Time Machine. Published in 1895, there are really 4 dimensions, 3 which we call the 3 planes of space, and a 4th, time. Minkowski turned all events into mathematical coordinates in 4 dimensions, with time as the 4th dimension. This permitted transformations to occur, but the mathematical relationships between the events remained invariant. Minkowski dramatically announced his new mathematical approach in a lecture in 1908. The views of space and time which I wish to lay before you have sprung from the soil of experimental physics, and therein lies their strength, he said. They are radical. Henceforth space by itself, and time by itself, are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Einstein, who was still not yet enamored of math, at one point described Minkowski's work as superfluous learnedness and joked, "Since the mathematicians have grabbed hold of the theory of relativity, I myself no longer understand it." But he in fact came to admire Minkowski's handiwork and wrote a section about it in his popular 1916 book on relativity. What a wonderful collaboration it could have been! But at the end of 1908, Minkowski was taken to the hospital, fatally stricken with peritonitis. Legend has it that he declared, "What a pity that I have to die in the age of relativity's development." Once again, it's worth asking why Einstein discovered a new theory and his contemporaries did not. Both Lorentz and Poincaré had already come up with many of the components of Einstein's theory. Poincaré even questioned the absolute nature of time. But neither Lorentz nor Poincaré made the full leap, that there is no need to posit an ether, that there is no absolute rest, that time is relative based on an observer's motion, and so is space. Both men, the physicist Kip Thorne says, were groping toward the same revision of our notions of space and time as Einstein, but they were groping through a fog of misperceptions foisted on them by Newtonian physics. Einstein, by contrast, was able to cast off Newtonian misconceptions. His conviction that the universe loves simplification and beauty, and his willingness to be guided by this conviction, even if it meant destroying the foundations of Newtonian physics, led him, with a clarity of thought that others could not match, to his new description of space and time. Poincaré never made the connection between the relativity of simultaneity and the relativity of time, and he drew back when on the brink of understanding the full ramifications of his ideas about local time. Why did he hesitate? Despite his interesting insights, he was too much of a traditionalist in physics to display the rebellious streak ingrained in the unknown patent examiner. When he came to the decisive step, his nerve failed him and he clung to old habits of thought and familiar ideas of space and time. Banesh Hoffman said of Poincaré, "If this seems surprising, it is because we underestimate the boldness of Einstein in stating the principle of relativity as an axiom and, by keeping faith with it, changing our notion of space and time." A clear explanation of Poincaré's limitations and Einstein's boldness comes from one of Einstein's successors as a theoretical physicist at the Institute for Advanced Studies in Princeton, Freeman Dyson. The essential difference between Poincaré and Einstein was that Poincaré was by temperament conservative and Einstein was by temperament revolutionary. When Poincaré looked for a new theory of electromagnetism, he tried to preserve as much as he could of the old. He loved the ether and continued to believe in it, even when his own theory showed that it was unobservable. His version of relativity theory was a patchwork quilt. The new idea of local time, depending on the motion of the observer, was patched onto the old framework of absolute space and time defined by a rigid and immovable ether. Einstein, on the other hand, saw the old framework as cumbersome and unnecessary and was delighted to be rid of it. His version of the theory was simpler and more elegant. There was no absolute space and time, and there was no ether. All the complicated explanations of electric and magnetic forces as elastic stresses in the ether could be swept into the dustbin of history, together with the famous old professors who still believed in them. As a result, Poincaré expressed a principle of relativity that contained certain similarities to Einstein's. But it had a fundamental difference. Poincaré retained the existence of the ether, and the speed of light was, for him, constant only when measured by those at rest to this presumed ether's frame of reference. Even more surprising and revealing is the fact that Lorentz and Poincaré never were able to make Einstein's leap even after they read his paper. Lorentz still clung to the existence of the ether and its at-rest frame of reference. In a lecture in 1913, which he reprinted in his 1920 book, The Relativity Principle, Lorentz said, according to Einstein, it is meaningless to speak of motion relative to the ether. He likewise denies the existence of absolute simultaneity. As far as this lecturer is concerned, he finds a certain satisfaction in the older interpretations, according to which the ether possesses at least some substantiality. Space and time can be sharply separated, and simultaneity without further specification can be spoken of. For his part, Poincaré seems never to have fully understood Einstein's breakthrough. Even in 1909, he was still insisting that relativity theory required a third postulate, which was that a body in motion suffers a deformation in the direction in which it was displaced. In fact, the contraction of rods is not, as Einstein showed, some separate hypothesis involving a real deformation, but rather the consequence of accepting Einstein's theory of relativity. Until his death in 1912, Poincaré never fully gave up the concept of the ether or the notion of absolute rest. Instead, he spoke of the adoption of the principle of relativity according to Lorentz. He never fully understood or accepted the basis of Einstein's theory. Poincaré stood steadfast and held to his position that in the world of perceptions there was an absoluteness of simultaneity, notes the science historian Arthur I. Miller. His partner, "How happy and proud I will be when the two of us together will have brought our work on the relative motion to a conclusion." Einstein had written his lover Mileva Mari back in 1901. Now it had been brought to that conclusion, and Einstein was so exhausted when he finished a draft in June that his body buckled and he went to bed for 2 weeks, while Mari checked the article again and again. Then they did something unusual. They celebrated together. As soon as he finished all 4 of the papers that he had promised in his memorable letter to Conrad Habit, he sent his old colleague from the Olympia Academy another missive, this one a postcard signed by his wife as well. It read in full, "Both of us, alas, dead drunk under the table." All of which raises a question more subtle and contentious than that posed by the influences of Lawrence and Poincaré. What was Miliva Mari's role? That August, they took a vacation together in Serbia to see her friends and family. While there, Mari was proud and also willing to accept part of the credit. "Not long ago we finished a very significant work that will make my husband world famous," she told her father, according to stories later recorded there. Their relationship seemed restored, for the time being, and Einstein happily praised his wife's help. "I need my wife," he told her friends in Serbia. "She solves all the mathematical problems for me." Some have contended that Mari was a full-fledged collaborator, and there was even a report, later discredited, that an early draft version of his relativity paper had her name on it as well. At a 1990 conference in New Orleans, the American Association for the Advancement of Science held a panel on the issue at which Evan Walker, a physicist and cancer researcher from Maryland, debated John Stahel, the leader of the Einstein Papers Project. Walker presented the various letters referring to our work, and Stahel replied that such phrases were clearly romantic politeness and that there was no evidence at all that she contributed any ideas of her own. The controversy, understandably, fascinated both scientists and the press. Columnist Ellen Goodman wrote a wry commentary in the Boston Globe, in which she judiciously laid out the evidence. And The Economist did a story headlined, "The Relative Importance of Mrs. Einstein." Another conference followed in 1994 at the University of Novi Sad, where organizer Professor Rastko Magli contended that it was time to emphasize Miliva's merit in order to ensure a deserved place in the history of science for her. The public discussion culminated with a PBS documentary, Einstein's Wife, in 2003, that was generally balanced, although it gave unwarranted credence to the report that her name had been on the original manuscript. From all the evidence, Mari was a sounding board, though not as important in that role as Besso. She also helped check his math, although there is no evidence that she came up with any of the mathematical concepts. In addition, she encouraged him and, what at times was more difficult, put up with him, for both the sake of colorful history and the emotional resonance it would have. It would be fun if we could go even further than this. But instead, we must follow the less exciting course of being confined to the evidence. None of their many letters, to each other or to friends, mentions a single instance of an idea or creative concept relating to relativity that came from Mari. Nor did she ever, even to her family and close friends while in the throes of their bitter divorce, claim to have made any substantive contributions to Einstein's theories. Her son Hans Albert, who remained devoted to her and lived with her during the divorce, gave his own version that was reflected in a book by Peter Michel Moore. And it seems to reflect what Mari told her son. Miliva helped him solve certain mathematical problems, but no one could assist with the creative work, the flow of ideas. There is, in fact, no need to exaggerate Mari's contributions in order to admire, honor, and sympathize with her as a pioneer. To give her credit beyond what she ever claimed, says the science historian Gerald Holton, only detracts both from her real and significant place in history and from the tragic unfulfillment of her early hopes and promise. Einstein admired the pluck and courage of a feisty female physicist who had emerged from a land where women were generally not allowed to go into that field. Nowadays, when the same issues still reverberate across a century of time, the courage that Mari displayed by entering and competing in the male-dominated world of physics and math is what should earn her an admired spot in the annals of scientific history. This she deserves without inflating the importance of her collaboration on the special theory of relativity. The E=mc2 coda, September 1905. Einstein had raised the curtain on his miracle year in his letter to his Olympia Academy mate Conrad Habigt, and he celebrated its climax with his one-sentence drunken postcard to him. In September, he wrote yet another letter to Habigt, this one trying to entice him to come work at the patent office. Einstein's reputation as a lone wolf was somewhat artificial. "Perhaps it would be possible to smuggle you in among the patent slaves," he said. "You probably would find it relatively pleasant. Would you actually be ready and willing to come? Keep in mind that besides the 8 hours of work, each day also has 8 hours for fooling around, and then there's also Sunday. I would love to have you here." As with his letter 6 months earlier, Einstein went on to reveal quite casually a momentous scientific breakthrough, one that would be expressed by the most famous equation in all of science. One more consequence of the electrodynamics paper has also crossed my mind, namely, the relativity principle, together with Maxwell's equations, requires that mass be a direct measure of the energy contained in a body. Light carries mass with it. With the case of radium, there should be a noticeable reduction of mass. The thought is amusing and seductive, but for all I know, the good Lord might be laughing at the whole matter and might have been leading me up the garden path. Einstein developed the idea with a beautiful simplicity. The paper that the Annalender Physik received from him on September 27, 1905, "Does the inertia of a body depend on its energy content?" involved only 3 steps that filled merely 3 pages. Referring back to his special relativity paper, he declared, "The results of an electrodynamic investigation recently published by me in this journal lead to a very interesting conclusion, which will be derived here." Once again, he was deducing a theory from principles and postulates, not trying to explain the empirical data that experimental physicists studying cathode rays had begun to gather about the relation of mass to the velocity of particles. Coupling Maxwell's theory with the relativity theory, he began, not surprisingly, with a thought experiment. He calculated the properties of 2 light pulses emitted in opposite directions by a body at rest. He then calculated the properties of these light pulses when observed from a moving frame of reference. From this, he came up with equations regarding the relationship between speed and mass. The result was an elegant conclusion. Mass and energy are different manifestations of the same thing. There is a fundamental interchangeability between the two. As he put it in his paper, the mass of a body is a measure of its energy content. The formula he used to describe this relationship was also strikingly simple. If a body emits the energy L in the form of radiation, its mass decreases by L/V2. Or, to express the same equation in a different manner, L equals mv2. Einstein used the letter L to represent energy until 1912, when he crossed it out in a manuscript and replaced it with a more common E. He also used V to represent the velocity of light, before changing to the more common C. So, using the letters that soon became standard, Einstein had come up with his memorable equation: E equals mc2 energy equals mass times the square of the speed of light. The speed of light, of course, is huge. Squared, it is almost inconceivably bigger. That is why a tiny amount of matter, if converted completely into energy, has an enormous punch. A kilogram of mass would convert into approximately 25 billion kilowatt-hours of electricity. More vividly, the energy in the mass of one raisin could supply most of New York City's energy needs for a day. As usual, Einstein ended by proposing experimental ways to confirm the theory he had just derived. "Perhaps it will prove possible," he wrote, "to test this theory using bodies whose energy content is variable to a high degree, e.g., salts of radium." Thanks you guy for watching this video. Thanks you guy for take your time watching this video. Have a great day.